All right, so like I said, we have our weld defects unit. I like to do this now because we played with welding a bit. Yes, sir. Pardon? Yeah, so basically what it's doing is it's helping us identify between good and a bad weld, and it's going to tell us what to look for. So while we're doing this, it's pretty easy, but if you don't know what to look for in a bad weld, it makes things a little difficult for you. Questions, but a lot of times you guys can answer those questions for yourself, especially if we know what to look for when we're welding. So that is the intent of today. So we see it's located within our 1048 unit, semi-auto automated welding. We have weld defects. It's going to be under this main title. You're going to pop that open. You're going to get weld defects PowerPoint, which we're going to watch today. Common weld defects video, and then an assignment, weld defects in the wild. And that's an assignment I'm going to give to you guys here. So you can grab my glasses. It's a little easier to read off the screen that way. So this is all open and available to you. You'll be able to see it. And what I'm going to do is I'm going to start screen share with this crew, and we will get this going. So we're going to open up the weld defects PowerPoint. We'll pop out of here. We'll get this into Google Drive, open with Google Slides, and then we will present it. Presenting it's going to give us a better view. So if you guys are viewing this at home on your own time, this is the best way to be viewing it. So weld preparation and defects. I'm going to shrink this, tuck this down the bottom of the corner here. Should be out of my way. Weld preparation is one of the biggest parts of our weld. It's our basis. It's where we start from. If we don't prepare our welds nicely, we're going to be fighting that weld the whole time instead of developing skills. So if we're putting plates together and they're all cockeyed, there's big gaps between them, that is definitely not ideal. What we're looking for is that nice, clean, tight fit up, looking like a stair set with no gaps. That way, you have maximized your chance to assess your welding and your welding only. Because if you got a bad fit up and you weld on it, you got multiple factors taking place now. You got your welding and you got your fit up as a factor. So we want to eliminate that fit up factor there. Just work with one variable at a time. So nice little saying here, if you fail to prepare your weld, you're preparing to fail. If you fail to prepare to fail is kind of an old saying. I just adapted it for the welding world. So preparation for welding. Basically, bad preparation can cause an inaccurate finished product, excessive internal stress, structural discontinuities, and weld flaws from bad cleaning practices. So we're pretty fortunate here with our steel, how it's nice and clean. For the most part, I do cut it in the saw. There may be some residue from the saw on it, but it hasn't been left exposed to the elements. There should be no real oil, dirt, grime, grease, whatever it is on it. But still, I have that buffing wheel at the back, that grinder set up with the buffing wheels to help clean our steel, because the cleaner it is, the nicer it's going to weld, the better it's going to look overall as our end product. So we're going to talk about some different ways we can end up with some discontinuities or some issues with our welds. So here we have flame and CACA cuts. So CACA stands for carbon arc cutting with air. Carbon arc gouging. So I call it gouging. That's the way it's just known. But the technical term is carbon arc cutting. With A is air assisted, because we use air to blow away everything we're cutting out. So that's why you can see in the picture on the right side there, all those sparks flying away. that gun or the electrode holder that that person is using has a big red handle. It's like a regular electrode holder, but bigger. And then beneath that rod, which it actually uses a rod just like welding, but a different type of rod, there's 3 air jets that go underneath it. And when your rod heats up the steel, the air jets blow it away. And that's why you get that big flying arc of sparks. And on the left, this is what your cuts are going to look like if you're using a 1/4 inch round cutting rod. So that's pretty cool. It's a neat setup. I've used it a ton. It's great for fixing things like cracks or cutting out welds on something that has to be removed. So I use it a lot when I was doing repair. With this though, like it says here, always grind the slag off of a carbon arc cutting, air assisted and oxy-fuel cuts because they leave a residual carbon and slag deposit. Slag isn't steel, that's burnt up oxidized steel. We don't want it anywhere near our welds, so we grind that off. Carbon, excessive carbon in our welds can cause hardening, and that can lead to all sorts of things like cracks and failures down the way. So not good. So what I do is grind that off, and then after that, I take my torch, I crank it right up so I get that nice blue flame, and I run it over anything I've ground or anything I've cut with carbon arc or with the torch, because that will help burn off the excess carbon. You'll see it sparkle when it burns, kind of like a sparkler, and you don't want a lot of that in your weld. So we also have dimensional faults. Dimensional faults could be from applying excessive amounts of heat to a thin material. Here's a great example. So on our slideshow here, we got a chunk of aluminum, a couple pieces welded to it, and you see that thing looks like a lasagna noodle that's been cooked. Definitely is not flat anymore. So knowing how to maintain straight pieces of steel, not put too much heat in here, and heat causes warping and distortion, especially on thin stuff. So when we're welding with thin material, we want to put as little heat into it as possible. So MIG is a great, or gas metal arc welding is great for thin sheet metal. If you turn it down low, you run a small wire. Gas metal arc welding is one of the processes that puts the least amount of heat into things, because you think of it, shielded metal arc welding is going to be much hotter. Flux core arc welding is way hotter. TIG welding is pretty darn hot too. So something that puts in a little bit of heat, such as gas metal arc welding, is going to be something I would probably choose, maybe TIG. And then we got to look at our application. I don't know what this is being used for, but the question I'm going to ask is, do we have to weld the whole thing? Do we have to have that much weld on it? If not, then we don't need to put that much weld on it, because more weld equals more heat and more distortion. So if this is just something that needs to sit there for a little bit, put a little tack on either end, maybe a 1-inch stitch on it, it'll hold it there just fine. If it has to be welded fully, then we got to look at other ways of controlling the heat input. It could be securing the plate, could be clamping it down, could be stress relieving after the fact. There's a bunch of options here, but yeah, we got distortion, we got warpage, we got all sorts of things. So to avoid this, you want accuracy of prep. So if you're hand cutting this for some reason and you have to put it on this plate, you don't want to cut with a big gap here that you got to fill up with weld, because obviously more weld is more heat. So if you get those joints nice and tight, you can put a small weld on there, even less heat input. So that's fantastic. Another way is adhering to weld specs and procedures. Use jigs and braces if needed. That's going to hold that material down, keep it aligned for you. It's another way of helping prevent warping and distortion. So we got some dimensional defects after welding. So we're looking at the finished weld here. And all these pieces are going to be, we have here labeled desirable fillet weld profiles, acceptable, defective. Then we got acceptable butt weld profiles and defects here. So desirable weld fillets, we have a concave fillet here. So if you look from this corner to this corner and we drew a straight line across there, it's a little bit concave and below that line. That is okay, as long as your weld is the correct size. You need to have it. This concave profile is going to help with stresses. Stresses are going to flow a lot nicer and easier here. With this one here, how we have a perfectly flat weld, we don't have a hard turn here in the corner or a hard turn here on the corner where the 45-degree sign is. But if we're drawing stress lines from the top of this weld down through the weld and out here, there would be a couple kind of corners on the road. Whereas this one, if we look at it, this is almost like a big corner on a road where you just lightly turn the wheel and you're driving along and you take a big long corner, but you still turn 90 degrees, right? So with this one here, this isn't one big easy corner. It's actually two little turns in the middle of there. So you drive straight, you turn a bit, you drive straight, you turn a bit. Still not bad. If we're looking at something like a weld defect where it's got hard edges or undercut, a lot of these aren't going to be that simple, easy turn anymore. When we're looking here, we got a notch effect here. We have all sorts of bad, we got undercut, different things like that. So the big thing with stresses and desirable weld fillet profiles is not having that hard notch on the edges of your weld. Because stress is like a car, it wants to travel, it wants to flow. And if you're hitting a hard corner, it's kind of like driving down to the end of a straight road, hitting the brakes, turning left, turn left, and then accelerate. So you got to make that stop, you got to turn, then you got to go. It's a lot more work than just that smooth big corner, right? And that's kind of how stress creates fractures. We'll get into that in a little bit, but basically, if your welds look like this top one, or even like this, those are fine as long as your weld meets your specified size. I don't really give you a specified size for weld in here. I'm focusing more on the basics. SATE will, if you do attend SATE for welding, they will teach you about specified weld sizes and all that stuff. Basically, long story short, easy flowing, good, hard corners and notches, bad. So some of the things we could see, dimensional defects, could be too concave, too convex. We could have overlap, cold lap. We could have undercut also. Convex welds. So convex is the opposite of concave. Concave is like a skateboard, how it's got a little bit of a curve in the middle of it. If you put a straight edge over it, you can see there's that little space, that air gap, that curve in it. That curve is there on skateboards, so you can flick it with your toe, do your kick flips. Otherwise, with a flat board, you wouldn't be able to do that very well. So convex is the opposite of that. It's a big hump in the middle of your weld. Too much of that is going to create stress right on the corners. And that's where that notch effect is going to happen. You can see right here in this image, on the right side, we got that big dark spot there. That's a crack starting. On the left side, we got a little one here. That's a crack starting. There's porosity in that weld as well. You can see it right there. They also didn't get that wall. You can see it straight lined. That's a section of the bevel on the wall they didn't weld. And then on the bottom, we can see a couple issues as well where stresses would create cracks. So a nice little weld profile is awesome, but we want to generally stick to about 1/8 of an inch when it comes to reinforcement. Reinforcement is how high above the weld plate is the top of your weld. So excessively convex welds create a hard spot, creates a notching effect. We can see how it's kind of been exploited there and bent a bit and has cracked the plate. It also increases stress in the weld zone, set up by shrinkage, concavity, and insufficient throat. So if we drew a line right there, you can see that this weld is concave. It's got that skateboard shape to it. Not good, because technically that weld doesn't exist. Weld by definition and standards does not start until it breaks the plane of the two pieces you're welding. So this would be unacceptable. The green line over there with a little bit of convexity would be just fine. You can fix it that way. Here you can put 3 stringers in, and that's what this person's done to correct that. Sometimes you want a concave fillet weld though. Like I said, if it's on something like a crane that's got lots of stresses and forces, you want to have that. You want to have that weld be able to flow there and not hit a hard corner and create a crack in there. Then that crane falls over and ends up on YouTube. We don't want that. That is something scary. And I would never be a crane operator just because you never know about things like that. And you're not going to inspect every single weld on your crane every day. Excessively concave fillet welds give a deceptive appearance as to actual size. Weld size does not meet specs. The strength is low. Notching effect can happen, and undercut is more likely. So the way they actually measure these welds, guys, is if you're given a spec, it says they want a 10 mil or an 8 mil effective throat. So an effective throat is drawn from the very deep throat of the weld right through the center of the face. That's going to be our face. But the way we measure welds is we draw the biggest right angle triangle we can within this weld section. So it would basically be from here to here, because you could draw that straight line there to there. This little excess that sticks out past here and past here doesn't matter. It's not included in the overall weld. That's basically extra weld you don't need. But if this weld was to be flat or even a little convex, we may be able to increase that dimension, say to 12 millimeters or whatever it is from 10. That's how measuring welding works. It's kind of a quick little demo. I don't hit it too hard in the 10 level. It's not that important for us right now. Cold lap. So that's when you have a whole bunch of steel falling down onto another piece of steel, but not actually sticking. I've got a great example of that right here. I'm going to pass around, see if I can find it somewhere in here. Might take me a second to find it, but yeah. So I've written this as lack of fusion, but it's also called cold lap. Have a look at the very bottom of that weld. So this person had a bad weld angle, and they put a great big weld on that plate, and it didn't actually stick. That's because a bunch of it rolled over the edge, and the arc was pointed, say, back here, and there wasn't a whole lot of heat heating up the base metal, but that steel just kind of rolled over and stuck to the base metal. And then when we cooled it down, it actually lifted and separated from that plate. So cold lap is a bad thing. It looks like a weld, but it has zero strength. And here's a great example of cold lap on a baby and a Shar-Pei puppy. As you can see, we got them nice little wrinkles everywhere. You know, that is what basically cold lap is a wrinkle in the steel or excessive steel rolled onto the next bit of steel, but there's no bond between those. So undercut. We have kind of talked about undercut a little bit. That's when we weld quickly. The arc force removes some steel from the plate, but we don't quite fill it back in with our filler metal. It is a major weld defect and probably one of the most common. The solutions to that are just welding a little slower, hanging out a little bit longer if it's a vertical weld, and filling in everything you removed with the arc, because the arc kind of cuts away material and then fills it back in with weld material. That's how we get the good penetration. That's how we know we've got good penetration, because of the thing there. Yeah, so it's probably the most common, and it's pretty much seen on every weld that's in here. And you know what? It's something we got to learn to deal with. It's as we progress through the years, we'll learn how to weld, getting less undercut, and eventually we'll have really nice welds. So internal undercut can cause slag inclusion. We can get internal on the inside doing a groove weld, but that's a 20 level thing. So we're going to move on. Undercut is definitely a weld fault, though, and we want to try and avoid it. So here, right here, we got what's called double undercut. Now, this person looks like they're welding way too hot. So we got a big section there and a big section there. This should be, oh, that's terrible drawing, but should be filled in. So if we were to apply a bunch of stress here, or we had some stress coming through here, first it would hit this notch and it'd probably start cracking there. It would travel through, hit this, and this probably crack there. So there's a chance this could crack right through to here. That could shear off. This could crack through down to there. That could break off. Basically, this is all sorts of bad. Couple corrective things we could do is, if we're allowed to, put a weld in here, fill that in, put a weld pass right there to fill that in. That is, if it's allowable. Yes, Philip. Yes, you can. So that's how we'd address those. But the best way to do it is to avoid it in the first place. Because if you got to go back and weld on this weld that you've already completed, in the eyes of your employer, you're costing them more for the same job you should have had done the first time. So that's going to be kind of a strike against you in the welding world. Here, we got a couple examples of undercut. So this is a single bevel weld that wasn't quite filled in. We got a big empty hollow here, big hollow here. This is going to crack right across. This might crack down through here. Maybe this will meet up. I'm not too sure, but it's pretty easy to see where the bad thing is going to happen on that weld. So we got some surface defects. We're going to rip through some of the stuff here. Surface porosity. Your weld looks like an arrow bar. It's got holes all through it. A bunch of stuff causes that, mainly moisture and stuff getting trapped in your weld. Bad shaped weld, ripples in the weld. Surface porosity also, if you're doing gas mill arc welding and you don't have any gas coverage, that's what you get, surface porosity. That's those holes. Badly shaped weld, ripples in the weld. It just doesn't look nice. It's not aesthetically pleasing. A whole bunch of nice C-shaped ripples in your weld the whole way across tells me you got good travel speed, good control of everything. If I see a whole bunch of V's and then some C's and then big weld, little weld, it tells me there's a lot of inconsistencies as you're traveling. Excessive spatter. We've all got those little dots of metal that stick to our weld. Well, if you get a whole bunch of them, that tells me something's wrong with either your angle or your machine. Craters. Craters are at the end of our plate when we rip that weld out of there or the wire out of there. And you see that little circular line on the end, or the circular hole on the end of your weld. That's a crater. That's also a weld defect. Stray arcs. If you're working with stick and you've got a passive helmet and you're just taking the rod and tapping everything in sight, and you got all these little spots look like acne all over your weld, that is a defect, because that can actually harden the steel and create cracks eventually if it's under a lot of stress. Ugly on the outside. Kind of like this fellow right here. I don't know whether that's a cat or a dog, but I know it's not the most pretty. So if that was a weld, that would be a pretty bad weld, I would say, in my opinion. Porosity. So we talked about those holes. Well, the nice thing is we got a bunch of x-ray pictures here and what it looks like on an x-ray. So you see the holes there, they're going to show up right here. Cracking. So they can either go longitudinal down the length of the weld or transverse, which is across the weld. And those can occur in different ways, but also bad things. We don't want those. So we have things here like insufficient fill on a root. Those little dark spots are where there is a lack of weld, and that's a defect there. Oops. Second picture, we have internal or root bead undercuts. So when we get in the 20 level, we start working with bevel plates and welding the back side of the plate here from the front side. You weld from the top all the way down through, weld this back nice, and then you start filling this all up and learn how to do that. It's pretty cool. It's a neat process, but we can get undercut when doing that. And on an x-ray, that is what that's going to look like. So we got some internal defects. Talk about some of these. Laminar could be part of the steel. This could separate in layers. Spherical could be round like little pinholes. Could be tungsten inclusions. Could be nitrogen trapped in your weld. Could be moisture. Could be anything. Lots of stuff going on there if we don't have a clean weld. Laminar defects are cracks, insufficient penetration. You know, it might look good on the outside, but it might be hiding some pretty bad secrets on the inside, right? And once again, an arrow bar. Looks great on the outside, but you crack her open and you got all those holes in the middle. Let's just hope our welds don't look like that. So oxides, we can get stuff trapped in our weld. We can get porosity. We can see those pictures. Slag inclusions. We got tungsten inclusions. Tungsten glows like stars. Tungsten is much harder than the steel we're working with. But when you're doing TIG welding, you'll be walking that electrode side to side, and sometimes you touch the steel and you'll wiggle it quickly and then fire up the arc and keep on going. Well, a little bit of tungsten gets stuck in your weld, and that's going to glow every time on an X-ray, because it's so hard, it just reflects all that back to the film, it exposes, and that's how it shows up. Definitely not something you want. Laminar defects, so cracks. As we can see here, we got some examples of cracks on fillet welds. This one is separate, cracked right around the back, separated from the plate. This one is cracked on either side of the bevel, and the one on the right is just cracked right off that plate, all in all. So we want to make sure that our electrode angle includes both metals we're trying to work with, our base metal and whatever pieces we're attaching with. Inadequate or lack of penetration. So if we're doing groove welds, we don't get all the way through, it's going to look like that X-ray on the top if we're X-raying things. Offset or mismatch, it happens. That's a bad fit up. Sometimes it's unavoidable, but in here, it is completely avoidable. We have all the opportunity in the world to set ourselves up nicely in here. So fit up is something I'm always going to be on. Fit up and prep, I'll always be talking about it. You guys will get tired of it until you guys get it all right, and then I won't have to mention it anymore. Spherical defects, little round things in our weld. So we got gas bubbles, we got porosity, we got all sorts of things in there that we don't want. All bad. Basically, your weld should be 100% weld metal and base metal mixture through and through, with nothing included whatsoever in it. Causes of porosity. So this is going to be relevant to us. Surface contaminants. Like I said, junk on your weld. Get rid of it. Grind it off. You don't want to be burning oil, paint, galvanizing, scale, any of that stuff. It's bad for you. So if we grind it off, then we don't have to worry about turning that into a harmful gas. Lack of shielding gas. You guys forget to turn on your bottle. You guys come up and you say, Mr. Scott, what's wrong with this weld? And like I said, I can hear he doesn't have his gas bottle on. Sounds like ripping a wet cotton t-shirt versus that nice, hard, sharp electrical kind of crackle it should have. That one's one of the most common. Then you got a dirty tip. You're not getting the gas to the weld properly. Slag entrapment, you get junk in your weld, probably by bad manipulation of your gun and your electrode. Tungsten inclusion, we don't have to worry about that because we're not TIG welding, but it is a thing and it can happen. Copper and carbon inclusion from carbon arc cutting operations. We're not doing that really, but we are going to play with the plasma and the torch at some point in here. Hopefully, I want to get a day in before we get out of here. So we got all sorts of things happening here. We got oxidization caused by lack of shielding gas. We got a big defect in the back there. Looks like we got a miner in there. He's checking things out. We got examples of where all these things can happen. We'll get further into this in the 20 level. Crater cracking. It's when you rip that rod out of the end of a weld and you got that depression in the middle of or the end of the weld. That is crater. Kind of looks like a pothole. So way to deal with that is to finish up and hold that rod over the end of the weld just for a second before we finish that up. All right, and that is that for that. So what we have here is 11:50, which is 10 minutes till lunch. Awesome. So that gives me just enough time to go over an assignment with you. So we went through this. There is going to be a quiz on this at some point, but right now I'm going to get you into the weld defects in the wild assignment. So the weld defects in the wild assignment is, let's blow this up a little bit for you guys so you can see it. For this assignment, you'll need your phone and you're going to need a good internet connection. You'll be assigned one of the common weld defects. Basically, I'm not going to assign you a weld defect. I'm just going to have you look for a weld defect. And what this is in your travels, at home, on the bus, at the park, wherever you go, if it's to the mall, but please don't go to the mall. That's the super spreader central. With the numbers on the rise, we want to be really cognizant of where we're going, what we're doing. Some of you may think, oh, I don't have any welds at home. Well, everything has a lot of weld on it. Even the chairs you're sitting on, the frames are welded together. So this assignment basically gets you looking at some welds out in the real world. I want you to find a defect with one of the welds. Could be ugly, could have undercut, could have porosity, could have a big crater at the end of it. Could be a cracked weld. I don't care. Find me something. But once you have your defect, once you found it, snap a picture of it with your phone. After that, we're going to name the welding process used. So we're going to try and figure out which process it was that was used. Whether it was a stick weld, because we know what stick welds look like a little bit. Whether it was a wire weld, we know what those look like. If you don't know what it looks like, that's fine, but just put a guess in there. Point out the defect if it's not obvious. If it's not a great big crack down the middle of it and it's just one tiny little defect, throw it up in your editing app, draw an arrow, point to it, tell me what it is or where it is. And then we have a Dropbox here. Submit it to the Weld Defects Dropbox. That's going to be under assessments. You'll click that. There'll be a Dropbox. There should only be one of them. Drop it in there, and that is the assignment. I don't like to give homework, but that is going to be your assignment for the weekend. Honestly, it's going to take you about 3.5 minutes to do it. If you find a weld, like you can even flip up a stool at home. Like I don't want anything from in here because we got lots of stuff in here, but it's surprising how many defects are actually in the real world. I've worked a lot of places. One place I worked, quite public, everyone sees it every day, is Crowfoot LRT station. I helped put all the handrail up there, worked on the inside of the LRT where you come down off the top, down to ground level, the stuff going over Crowchild or Crowfoot or whatever street that is, I can't remember. All that steel, I helped put that in. I did a whole bunch of handrail there. And when I was putting some of that stuff in, I noticed there's some pretty bad welds on some stuff. Stuff that I would never personally deliver to a customer. But there's plenty of examples out there. You get on the bus, you're sitting there and there's a steel on the handrails. That's all really nicely TIG welded. Every now and then you find a bad one. So there could be a place to look right there. The window frames in here are welded. Desks, if you got a steel desk at home, there's this weld is in everything, everywhere. So it should be easy to complete this. My goal is to get you out looking at some welds in the world with a critical eye and trying to find me that defect. I found some really cool ones. I've had some students turn in some really neat stuff. And yeah, it's just interesting. I also like to know the location. So where you found the defect. So you say, oh, number 3 bus, number 3 sandstone heading to downtown on the seat or something like that. Cool. That's, a little bit of information. I marked this out of 3. Basically, give me the picture of the weld, the defect, where you found it, 3 marks, easy marks right there. And that's about 5% of your unit. So that is the easy thing. 11:55, we are done for the day. I'm gonna stop my Zoom recording and stop my share. I will get you guys to sanitize your seats and your spaces. And thank you for joining me for today's class. I really appreciate it.